Hello student, welcome to online lecture series. Today we will cover two topics of linear differentiable equation. That is the Bernoullis equation of the form dy by dx plus py is equal to q into y raised to n. And second one, dx upon dy plus p times x is equal to q, which is multiplied by x raised to n. Before we start the Bernoullis differentiable equation or the Bernoullis equation, we should know what is meant by linear equation. In the last lecture, we already saw what is meant by linear equations. The linear equation is in the form of dy by dx plus py is equal to q, or we can say that the another form of the linear differentiable equation is dx upon dy. So dx upon dy divided plus p times x is equal to q. In the first case, your p and q are function of x. P and q are function of x. The second case, where p and q are function of your y variable. This is the way in which we can express a linear differentiable equation in these two types. So according to the linear differentiable equation, we can find its general solution by finding its integrating factor. So we know that the linear differentiable equation in which a dependent variable and its first order derivative is present with index 1. So when this linear differentiable equation, this right hand side is a q, is multiplied with y raised to n, or in second equation, when the right hand side your q is multiplied with x raised to n, then the formation of this differentiable equation is said to be the Bernoullis differentiable equation. Then the Bernoullis differentiable equation is what? The differentiable equation in which first the linear differentiable equation is present and the right hand side is getting multiplied by y raised to n, where your p and q are function of x and the coefficient of your dy by dx is 1. This is the basic requirement of your linear differentiable equation. In this way, we can differentiate your linear differentiable equation and the Bernoullis differentiable equation. To solve such a differentiable equation, how to just find the solution, we can see the steps which is performed to find the solution of your linear differentiable equation, which is in the form of Bernoullis. The difference between your linear differentiable equation and Bernoullis differentiable equation is that the right hand side of differentiable equation is multiplied by y raised to n, means the dependent variable in that differentiable equation. So the steps involved in this particular solution, we have to just get the differentiable equation in the form of dy by dx plus p into y is equal to q, which is multiplied by y raised to n, where my y is dependent variable, p and q are function of x variable. And second step, we have to divide the entire differentiable equation by y raised to n. So dividing the differentiable equation by y raised to n, we get 1 upon y raised to n into dy by dx plus p y is divided by y raised to n is equal to q, because the entire differentiable equation is divided by this y raised to n, the new differentiable equation is occur. Then we have to make the adjustment. The y raised to n terms which is shifted in your numerator, we get y raised to minus n dy by dx plus p times y raised to 1 minus n is equal to q. This is the differentiable equation we have to convert this differentiable equation into linear differentiable equation. For that, we have to assume the coefficient of your p, that is your y, whose index is -1, y raised to 1 minus n. We have to assume this equal to u, another variable or another parameter. Then differentiating this, the given assumption y raised to 1 minus n is differentiated, we get 1 minus n, and index of your y is reduced by 1, so it becomes minus n. And again, the derivative of your y is dy by dx, and the derivative of your u is du by dx. In this way, we can find the derivative of your both the terms with respect to x. Then we have to replace all this value in the given linear differentiable equation, that is in equation number 2. So we get y raised to minus n dy by dx is equal to 1 upon 1 minus n du by dx. We calculated the value of your y raised to n dy by dx. This value, we have to put the value of your y raised to minus 1 dy by dx equal to whatever we find in our equation number 2. So replacing the value of replacing the value of these particular terms in the given equation, we get the new differentiable equation. It is a 1 upon 1 minus n du by dx plus pu is equal to 2. It is the linear differentiable equation in u. So we have to make the conversion. The coefficient of your du by dx should be 1. So entire differentiable equation can be multiplied by 1 minus n. So we got du by dx plus p 1 minus n u is equal to q 1 minus n, where 1 minus n are some real number. So when we just make the multiplication of this p with ur 1 minus n, we get suppose p1, and right hand side becomes suppose q1. So this is the linear differentiable equation in u. We have to find its general solution, and in the last lecture we already saw how to find the general solution of such a differentiable equation. We have to find its integrating factor. U is my variable in this particular example, so I have to find the integration of your p1 with respect to x, and it is a coefficient, it is the index of your exponential function. So integrating factor of this particular differentiable equation is e raised to integration of p1 dx. After finding the integrating factor, we have to multiply that differentiable equation, or we have to find the solution, and the solution can be found. The dependent variable is my u. Here, the dependent variable is my u. The u into e raised to integration p1 dx is equal to q1 integration p1 dx, again dx plus c. And lastly, replace the value of your u equal to whatever we assume. We get the differentiable equation solution when it is in the form of Bernoullis. In the similar way, the type number 2 is here. Instead of dx upon dy, the dx upon dy plus px is equal to q into x as to n. This equation is occur. Means the in the similar way, we can find the differentiable equation which is in the form of dx upon dy plus px, and the right hand side is multiplied by q is multiplied by x raised to n. So in a similar way, we have to just find its solution by dividing the entire differentiable equation by x raised to n. These are the steps involved, same as that of your type number first. Instead of your x, we have to just replace y, or y instead of y is replaced with x. So dividing the entire differentiable equation by x raised to n, we get the first step. That is step number second, in which after division we get x raised to minus 1 minus n dx upon dy plus p x raised to 1 minus n is equal to q. Then we have to put the value of your x raised to 1 minus n is equal to another variable, suppose u. That is defined here. Again, we have to differentiate this with respect to y, because our example containing dx upon dy. The differentiation of your x raised to 1 minus n is 1 minus n x raised to minus n dx upon dy is equal to du upon dx. Finding the value of your x raised to minus n dx upon dy is nothing but 1 upon 1 minus n du by dy. This is the value of your that particular coefficient of dx upon dy is x raised to minus n. Then next step, we have to just put the value of x raised to n minus n. This is the differentiable equation. Then we have to find its integrating factor just by making the coefficient of your du by dy is 1. That term is mentioned here. Then we have to find its integrating factor, taking the integration of your p with respect to y. And we are finding its solution. Means the type number 1 and type number 2 both are identical, in which we have to just only convert the given differentiable equation into the linear differentiable. Means the step involved in the conversion of your Bernoullis differentiable equation into linear differentiable equation by making your right hand side only the function of your x in type number first and function of y in type number second. If your y raised to n and x raised to n, the extra variable is multiplied your q, we have to shift it to the left hand side by dividing the entire differentiable equation by that index. And lastly, we can find the solution of this differentiable equation. Again, instead of your x, we can find we are finding the solution in terms of u and replacing the value of your u in terms of x. And the third and the fourth method or Bernoullis equations are again same. Only the change in that the coefficient of your dy by dx is the derivative of coefficient of your p. Means suppose the p is get multiplied with f of y, then its derivative is the coefficient of your dy by dx. The coefficient of your dy by dx is what? The coefficient of your p, its derivative. This is the type number 3. The type number 4 in which the dx upon dy, the coefficient of this dx upon dy is simply derivative of your function f of x. Again, the same condition arise. We have to just put the value of your f of y is equal to new variable, and that variable suppose u. We are assuming it's a f of u is equal to f of y is equal to u, taking its derivative with respect to x. The derivative of f of u, f of y becomes f dash of u y, and the derivative of your y becomes dava y upon dava x or dy by dx is equal to du by dx. And lastly, the putting the value of this assumed value, that is f of y is equal to u in the given differentiable equation. So we get the differentiable equation in variable u. And we know that how to find the integrating factor, the integration of your p with respect to x, and that particular terms becomes the index of your exponential function. So that the integrating factor of this differentiable equation is e, whose integration is p, integration of p into dx. And lastly, the general solution of such a differentiable equation can be solved, that is u into integrating factor is equal to q into integrating factor and its integration plus c. And lastly, replace the value of your u is equal to whatever we assume, we get a final solution of such a differentiable equation. So in this way, we can find the solution of the Bernoullis differentiable equation, which is in the form of f dash of y into dy by dx plus p of p into f of y is equal to q. The similar way, the type number 4, the variable y is dependent, it becomes independent, and independent variable x becomes dependent. The type number 4 is involved. That is a differentiable equation in the form of this, the dx upon dy, whose coefficient is f dash of x, and the p, whose coefficient is f of x. Again, p and q are the functions of y variable, or say p, it's a constant. Then we have to find its integrating factor by assuming f of x equal to some variable. This is my differentiable equation. This is in the type of f dash of x dx upon dy plus p into f of x is equal to q. Then we have to assume the value of f of x equal to u. Then f of x equal to u, we assume this value. Then we have to differentiate this f of u is equal to u with respect to y. Then we get the derivative of your f of x with respect to y is f dash of x. And the derivative of again x is equal to dx upon dy is equal to du by dy. Replacing the value of your f of x and f dash of x into dx upon dy, we get the linear differentiable equation in u. It's a linear differentiable equation in u. Then lastly, we have to find its general solution by finding its integrating factor. These are the steps involved. Means the type number 1 to type number 4 are the identical methods to find the Bernoullis differentiable equation in terms of linear differentiable equation and find its general solution. So the identification of such a differentiable equation is very easy. So we have to just check whether the right hand side is get multiplied by, suppose we will just summarize all these things here. This is the differentiable equation. The first is this. The dy by dx p of y, and this is y whose index is suppose n. It is the first type. Type number second. The example in the form of dx upon dy p into x, and q is multiplied by x raised to n. It's x raised to. So type number second. Type number third is here. Instead of your this f of y is multiplied here. It becomes dy by dx. And last is these are the four methods. So we have to just observe whether the right hand side is multiplied by x raised to n or y raised to n, or if the coefficient of your this p whose derivative is present as the coefficient of your dy by dx or dx upon dy. So according to that, we have to identify which particular method is applicable to simplify such a differentiable equation. So let me see some examples, then we will just get the idea. Here the example number first is here. Solve 2 dy by dx minus y sec x is equal to y cube into tan x. So when we observe this differentiable equation is not a linear, but it is a differentiable equation in the form of Bernoullis differentiable equation. Why? Because your right hand side is a function of only x, is multiplied by y raised to 3. Means y raised to n is here, y raised to 3. So we have to just divide our entire differentiable equation by y raised to 3. Our differentiable equation is here, then we have to divide the given differentiable equation. The differentiable in the form of this: p is equal to sec x, q equal to tan x, y raised to n is equal to y raised to 3, p equal to sec x, y equal to this minus y, means we are changing the sign of p with minus sign, and dy by dx. The 2 is extra here, 2 is the coefficient of your dy by dx. We can make the conversion into 1 by dividing your entire differentiable equation by 2. We have to divide the given differentiable equation by y raised to 3. Then we get this 2 upon y cube dy by dx minus y sec x divided by y cube is equal to y cube tan x upon y. So we have to just make the cancellation of your y index. Then the first coefficient of your dy by dx remains as it is. Is a 2 upon y cube dy by dx minus 1 upon y square into sec x. And the right hand side, it is a tan x. Means we are converting our differentiable equation of type number 1 to type number 3. Type number 1 to type number 3. Then we are converting this particular. So we have to just put the value of your minus 1 upon y square or simply 1 upon u square. 1 upon y square is equal to u. Then differentiating this with respect to x. The derivative of your u is du by dx. And the derivative of your 1 upon y square is minus 2 upon y cube. And the derivative of again y is dy by dx. So we have to just convert the Bernoullis differentiable equation in type number 3. Means the linear differentiable equation can be reduced by using your type number 3 by assuming the coefficient of your p. Where p is equal to sec x. We have to put the value for p is coefficient equal to new variables. So we have to replace all the value. Then this equation becomes du by dx is equal to minus 2y cube 2 divided by y cube dy by dx is the value of your du by dx. Means we are changing the value of here. 2 upon y cube dy by dx is replaced with du by dx, and that is present here. Again, the minus sign as it is. The value for u is equal to 1 upon y square. So 1 upon y square with minus sign as it is sec x tan x. But it is not a linear differentiable equation because the coefficient of your du upon dx should be 1. So we have to multiply your entire differentiable equation by minus sign. So after multiplying minus sign, we got du by dx plus u sec x is equal to minus tan x. It is the linear differentiable equation in u variable. That's a du by dx plus pu is equal to q. Then we have to find its integrating factor. The integrating factor can be found by taking the integration of your p with respect to x. Then we have to find its integrative value for p is equal to sec x. So we get the integrating factor of this particular example after taking the integration of your sec x. And integration of your sec x is equal to sec x plus tan x. Then next we know that e whose power is log is nothing but the terms which is present in your log function. So we get the integrating factor in the form of sec x plus tan x. And lastly, we have to find the solution. Solution can be found with the help of the formula. As a u is my variable of this differentiable equation is multiplied by integrating factor is equal to right hand side into integrating factor is integrated with respect to x plus c. So replacing the value of your f, value of your integrating factor and value for u is equal to 1 upon y square. We replace the value for u. We're replacing the value for integrating factor sec x plus tan x is equal to integration minus tan x is multiplied with sec x plus tan x into dx. When we make the simplification, the minus tan x into sec x becomes minus sec x into tan x. And tan x becomes tan square x. So we are making the integration separately of these two terms. The first integration with respect to x of tan x into sec x. And second, tan square integration separately with minus sign. And we know that tan square value in terms of sec is 1 minus sec square. Taking the integration of these particular terms, integration of your tan x into sec x, we have to find it. And again, the integration of your 1 and integration of sec square, we have to make the separate. Then the left hand side remains as it is. The integration of your tan x into sec x is minus sec x, due to the minus sign. Integration of your 1 is x, and integration of your sec square is tan x. This is the way in which we can find the solution of the linear differentiable equation, which is in the form of Bernoullis. The procedure is that the linear differentiable equation in the Bernoullis form, we have to convert into the type number 3 or type number 4 according to the dy by dx or dx upon dy is present. Then we have to just assume the coefficient of your p is equal to some new variable. Then we have to find its derivative and just replace all the values and find converting into linear differentiable equation. And lastly, taking the solution formula, putting the value of your integrating factor and value of your u, we get the final solution of this differentiable equation. In similar way, we can find the solution of the differentiable equation which is in the form of. This is the new example, and everybody will just understand what is the procedure to find the simplification of it. So first we have to make the conversion of this differentiable equation to linear differentiable equation. Then we have to make the simplification, the given differentiable equation in the form of this, but it is not a differentiable equation, linear differentiable equation. It is in the form of dy by dx plus py is equal to q times y raised to n. And we know the procedure how to find the solutions. This is the right hand side. This is the variable which I have to put here. We have to make the simplification, putting the value for y cube is equal to u, finding its derivative, then making the simplification. This procedure is very simple. So putting the value for u is equal to y cube, then du by dx becomes 3y square dy by dx. We have to put both the values in the differentiable equation. So we have to find dy by dx. The dy by dx is nothing but or 3y square dy by dx equal to du by dx. Putting the value here, so we get du by dx. This 2x remains as it is, and the value of your y cube is nothing but your u. And the right hand side is a function of only x, because it is not in the it is in the form of not it is a form of this. So not a Bernoullis equation. It is in writing type number 3. This is the form of my differentiable equation. So the f of y is nothing but the terms which is containing only y. When we observe here, the 2x is the value of your p, and y cube is your f of y. So we have to assume the value of your y, f of y is equal to u. So we put it the value, finding the derivative, then we get a conversion of a differentiable equation. We have to find its integrating factor. This is the last step example. So we get this differentiable equation. We have to find its integrating factor, where the value for p is equal to 2x. The value for q is equal to your right hand side. The integration of your 2x is nothing but simply x square upon 2 to get cancelled. The e raised to x square is my integrating factor. We have to find a solution where u is my dependent variable. So u into integrating factor is equal to q into integrating factor, and replacing the value for u and integrating factor. U is equal to what? U is equal to simply y cube. We will replace in the next step. Integrating factor e raised to x square. Again 4x e raised to minus x square e raised to x square. This is my function q, and this is my integrating factor. The integrating factor and the q that containing e raised to minus x square get cancelled. And in the next step, we will make the simplified form. That is a u e raised to x square integration 4x dx plus c. And we know that the integration of your 4x is 4 times x square upon 2, and at the same time we replace the value for y is equal u is equal to y cube. So 2 get cancelled, we get a final solution. In this way, we can find the simplification of the differentiable equation which is in the type number 1 or type number 2, type number 3, or type number. In a similar way, we can make the conversion of the linear differentiable equation, which is in the form of Bernoullis, into linear, and in finding its solution. So,